for a linear system, you know what a fundamental matrix is. The fundamental matrix, let's do a quick review. It is corresponding to a given linear system, and it is determined by the matrix A. And so we look at the homogeneous system. And suppose we put n solutions of the homogeneous system into a matrix. So you see the matrix G is formed by n columns. So first column, we call it gamma 1, gamma 2, and gamma n, the n columns of the fundamental matrix. They are solutions of homogeneous problem. So actually, this is the corresponding homogeneous problem. But they correspond to different initial data. So gamma 1 satisfies the homogeneous system with the initial data given by epsilon 1. You see, gamma 2 will be solution of the initial value problem subject to initial data epsilon 2. So what are these epsilon? Epsilon 1, epsilon 2, etc. So they are unit vectors. Yeah, they are unit vectors in Rn. So here, this is the homogeneous system, a linear system subject to an initial data given by epsilon j. So for this initial value problem, we denote its solution by gamma j. And after we solve these n initial value problems, and then we find the n solutions, because each gamma j is a solution, right, to an initial value problem. And then we get this matrix. You see, this is a matrix that we call the fundamental matrix. And this fundamental matrix is such a matrix that each column is a solution of an initial value problem. So let's look at specifically, if we write each column. So gamma 1, you see, because it's the first column, so we use this so that there are two subscripts. So this is the first column, right? So the gamma 1 is the first column of the fundamental matrix. So, and this gamma 1 has the first entry, second entry, third entry, and all the way to the nth entry of the gamma 1. So this is our gamma 1. And then similarly, this gamma 2, you see we use the second column, right? So gamma 2 is placed in the second column. And this is the first entry of this column. Second entry of this column. The last entry of gamma 2. So we use this notation. So this is gamma n. So this is the nth column of the fundamental matrix. Here, the first entry, second entry, and the last entry of this column. So here we see the very clearly, so to show some details for each column. And this fundamental matrix, and we know immediately this matrix satisfies initial data. So when t is 0, then each column evaluated at 0 will be a unit vector. So we can see this gamma 1, since it's a solution of that initial value problem with the initial data being epsilon 1. So gamma 2 at 0 will be epsilon 2. Gamma n at 0 will be epsilon n. So together, we have this fundamental matrix evaluated at 0 will be an identity matrix. So then immediately this matrix, we have that matrix equation. So we just see this, since each column, right, satisfies the equation, the homogeneous equation, then the entire matrix satisfies the homogeneous equation. Yeah, you see we have first column, second column. So each column of the fundamental matrix satisfies the homogeneous equation. Then we can quickly get the matrix. Because we know derivative of this matrix is simply derivative of each column. And if derivative of each column satisfies the homogeneous equation, and then we can take out the matrix, and then we can rewrite this A. This is the same as A times all those gamma. So we put A outside. So that part is the G, the fundamental matrix. So then we see that the derivative of G is A times G. So that means the fundamental matrix satisfies the matrix equation. The derivative of G is A equals G. So now we can write this fundamental matrix as a matrix satisfying the equation. The derivative of G is equal to this matrix A of T times G. And this G, this matrix, satisfies the initial data. So that is G at 0 is identity, is an identity matrix. So that's our fundamental matrix. And then if we look at if we just write the G, suppose the times a constant. What it means is that G, but a matrix, suppose G is a n by n matrix, then the C cannot be just a constant number value. It is a vector. So we can write in this form, C1, C2. So it's a column, right? G times a vector. This is actually, recall that G, we can write it as n columns, right? First column is gamma 1, second column is gamma 2, and then the last column is gamma n. So we write G matrix into that form and then times this vector. It is actually a linear combination of the columns. So gamma 1 as a vector valued function and the gamma 2 as another vector valued function. So we can write as a linear combination of n columns. So it's just to realize that G times a vector, the matrix times a vector, is actually, you see the C means a column vector, right, with n entries. And that column vector shows the combination, the weights for the combination of the columns. So G times C is just the n combination of the n columns. So if each column is a solution to the homogeneous problem, then this is also a solution to the homogeneous problem. So if you want to verify, if you want to check, double check, so suppose we have this problem, we're thinking of homogeneous system. So suppose each gamma j, right, is we know that j from 1 to n, they are solutions of this problem corresponding to different initial data. But each gamma j is a solution of the homogeneous problem. And then the linear combination, which we want to verify, is that G fundamental matrix times C is this vector. This vector, we know already this is a vector which is a linear combination of those gamma j. So this vector is also a solution of the homogeneous equation. We can double check. So what is this? So this derivative, this derivative means derivative with respect to t. So we just take derivative with respect to t times this column. And then derivative of the fundamental matrix, because we know it satisfies the homogeneous. So here we notice the derivative of the fundamental matrix is equal to A times the fundamental matrix, because the matrix itself satisfies the homogeneous equation. We just commented. So then we put a C there. C is still there. So we replace, and then we can realize that what do we see? What we see is this part, G and C together. Isn't that the same, right? G fundamental matrix times the C. So that is to show that this G times C is a solution of the homogeneous problem. Yes, so that shows if we substitute the GC into the equation, you see, in the place of X, then GC derivative equals A times GC. Yeah, we just see that this GC, right, in the place of X So the derivative of GC equals A times GC. So that shows the G times C is a solution of the homogeneous problem. So that is just a quick way to verify that and to recognize that whenever you have n fundamental, whenever you have the fundamental matrix, and this matrix times a vector, it's just the linear combinations of these columns, right? So this shows another, it's just any arbitrary combination of the columns is still a solution of this problem, of the homogeneous problem. So that is something to recognize. Yeah, just to recognize this is a solution. That means we have infinitely many solutions. Although we use only n solutions, right? We can generate arbitrary combinations of the n solutions. Then they are still solution of the homogeneous problem. So now we're going to see the importance of using the n solutions to even represent a non-homogeneous solution. So let's think of our non-homogeneous problem. So we're going to write x prime equals, and now add a certain vector b. b of t is not necessarily 0. So when it's not 0, it's a non-homogeneous problem. Since we can represent general solutions to the corresponding homogeneous problem, can we possibly represent a general solution to this non-homogeneous problem? So what we can do is to multiply both sides of the equation by the G inverse. That is the inverse matrix of the fundamental matrix. Actually, we can show that G is invertible. At least when T is 0, we see an identity matrix, right? That shows the independence of the n columns, at least when T is 0. So its inverse exists. So it is the inverse of fundamental matrix exists for n and t, where the solution of this problem, is defined. And then we multiply both sides by this. It's very much like a integrating factors approach. So we multiply this both sides of the equation by the inverse of the fundamental matrix. Well, what we can get is a new system. So G inverse T times left side and then G inverse T times equals G inverse T times B of T. Yeah, notice that I moved this term to the left side. So there's x prime minus that, AT times x. So only leave the B on the right-hand side. So then afterwards, we have two terms involving x, right? So because we move it to the left side. So we can see the two terms involving x, and then we multiply the inverse. So you recall that this, when we handle this problem, just think of a single equation case, because it doesn't hurt if you think of the single equation case. When we have just one single equation derivative minus some function times x equals b of t. That's a linear equation, right? Then what we do, we multiply it by the integrating factor. That integrating factor is e to the negative integral of a of t dt. So in single equation case, it's a special case. But now, this is very similar to that. So we use the inverse of a fundamental matrix, right, instead of that. But later you will realize we write the fundamental matrix in this form, T times A e to the TA. Yeah, so for the constant coefficient case. So now we just see that notation is not by chance. So we just realize, okay, here is the case that for single equation, if we can do this, actually we just treat the system in a similar way. So write the system first, put these two terms on one side, and then multiply both sides of the equation by inverse of the fundamental matrix. Yeah, and so that's what we're getting here. So times inverse. So the purpose of that is after you multiply that, the effect is very much like the technique of using integrating factors to find solution of a linear equation. So what we get is G inverse T times X derivative. It becomes derivative of one single term. Yeah, the other side becomes G inverse of T times B of T. Yeah, so that is when you from the given problem, right? So we multiplied both sides by G inverse T, the fundamental matrix, both sides, and then what we're getting is this. Yeah, do you realize the effect? Isn't that quantity very much like the integrating factors, right, for linear equations? Yes. So actually, so this two terms becomes one derivative of one term. And then we are going to solve. We can, okay, we will solve this one as antiderivative. So we do the integral of the G inverse T B of T integral from 0 to T. Of course, this is a dummy variable, so we can change the name. Instead of using T, we can say tau or sine. So it doesn't matter what you use. So I'm going to use a different letter, D sine. Okay, then plus C, which is the integration. It is a constant vector. So now one step, I think there's one thing to fix. It is this one without prime. Yeah, it is G inverse. Okay, so the G inverse, so times this is the quantity inside, right? Quantity, the whole thing, by doing the antiderivative, then we can find this quantity. So, and then this, our goal is to find X, the solution X for the non-homogeneous problem. So we're almost there as long as we multiply both sides of the current form by the G matrix fundamental. So this both sides, this other side also we multiply it by G fundamental matrix. So what we're getting, because G times G inverse will be identity. So this together is identity matrix. Identity times X is X. So we get X. So the left side is X. The right-hand side, G times C. So I'm going to put this term. So G times C, right? That's very easy to see that. G times C. So I'm put it here now. And then the other term will be G times this integral. Okay, so let's write G times that integral. Fundamental matrix G times the integral from 0 to T G inverse sine B at sine D integral at sine. So now we have two parts to represent a general solution to the non-homogeneous problem. So don't forget the problem we're solving is this non-homogeneous problem. And we see first part for the solution X is that this part, second part. Yeah, the first part is a solution to the homogeneous problem, right? C, whatever C you choose, C, a column vector, whatever C vector you use, and this is always a homogeneous solution. So if it's a homogeneous solution, then what is that one? And that one, you see, it is depending on B, the B vector. So let's choose a special case. That means we found a general solution for the non-homogeneous problem. The general solution is represented by this formula. And this formula has two parts. That means this representation is a solution to the non-homogeneous problem. And that means for whatever C, right? Any choice of this column, C, and it's going to be a solution to the non-homogeneous problem. So let's make a special case. When C is 0, what happens is that when C is 0, the 0 vector this matrix times the 0 vector will be 0. So then we're left with only this part. So that means this is a particular solution to non-homogeneous problem. So we recognize that as a particular solution. So let's denote the second part is just a particular solution to the non-homogeneous, because together it is a particular solution, right? So this second part corresponds to a solution when C is 0, when the vector C is 0. Yeah, it is a particular solution. But when C is not a 0, together that's still a solution, right? A solution to the non-homogeneous problem. Yeah, so actually we can see if you have a particular solution to the non-homogeneous problem, you can get many solutions to the non-homogeneous problem. So you add this part, which is a solution to the corresponding homogeneous problem. Yeah, so we have found a general solution to the non-homogeneous linear system. And from this examination of this representation formula, we realize a homogeneous solution can be added to the particular solution, and then the sum is still a solution to the non-homogeneous problem. So, okay, that is the meaning of this representation formula for our non-homogeneous case. So this formula gives a non-homogeneous solution, and it's a general solution. That means if you can find one solution for this non-homogeneous problem, you can find all solutions to the non-homogeneous problem. All you need is to find a general solution to homogeneous problem. So that, and we know the homogeneous, the general solution to the homogeneous problem is fundamental matrix times a C, right? C is arbitrary. Okay, so now we have solved actually a general, either homogeneous or non-homogeneous system of equations. In the following, I will simplify the system. Let's consider only the constant coefficient case. So for a linear system, right, no matter it is homogeneous or non-homogeneous, and we can now consider a simple case. What if I have A as a real valued matrix? It does not depend on T variable. So it is just this case with B even being 0. Let's just consider a constant coefficient matrix, and can we find its fundamental matrix? Certainly, all the previous discussions are applicable because this is just a special case. And that means, okay, let's look at one example. Okay, I will give you x prime. For example, I just have x derivative equals a. Suppose I have a as 1, 1, 0, -1 times x. right? So this is a constant coefficient matrix. So we can see that in this is in the form, right? X derivative equals a matrix A, which is not depending on T. Yeah, so in this case, how do we find fundamental matrix? Of course, you can still use the definition of the fundamental matrix and you can look for it. So for example, all you need is to determine the two columns, right? So this matrix, you first give this matrix and then let initial data being given as 1, 0. That way you get a solution because this initial value problem has a solution. We call it gamma 1. You see gamma 1, let's call it gamma, the first entry of gamma 1, second entry of gamma 1. Then you will find a solution to this problem. And this solution is actually possible if you just try. You will find it to be e to the t 0. And then you can find solution to another initial value problem, right? So let's just change the initial data. Then I will define another initial value problem. So suppose initial data is the other unit vector, then you have a different initial value problem. So you will solve that one, you will get gamma 2. Gamma 2, what we call it is first entry of gamma 2, second entry of gamma 2, and the solution is, in fact, half of e to the t minus e to the negative t. And the second entry is e to the negative t. Yeah, so at least after we solve this for gamma 1, gamma 2, then we can find fundamental matrix. And it's easy to check initial data. You see this when t is 0, when t is 0, right? That's a 1, 1, 0. Yeah, so, and satisfies equation can be also checked. Gamma 2, when t is 0, you see, this is a 0. And when t is 0, this is 1. So 0, 1. So gamma 1, gamma 2 satisfies different initial conditions and also the equation if you double check. Okay, so that's totally by our definition of the fundamental matrix. So after you have found it this way, but in case you want to try to solve it, so the hint is it's possible, right? If you write the first equation, for example, x1 derivative equals x1 plus x2. And second equation is x2. I'm trying to write this into two equations, right? You can see better that way. x2 derivative equals negative x2, right? So initial data, yeah. So you can also do that. So, but let's see if you look at the homogeneous equation,
And it's possible to use separation of variables method to get x2 first, right? So this dx2 over x2 is negative dt. You see, we do the separation of variables. We can possibly find x2 as a function of t, right? Then you do the integral, then you will have some integration constant. Then one constant will appear. And then you substitute x2 into this equation, you can solve for x1. So that is, after you do solve for x1, you can get another constant. So this one, eventually your solution curve, that is this solution curve x1, x2, after you solve this homogeneous problem, you have two arbitrary constants in the representation. But with initial data, then you can determine those constants. So that's how we find gamma 1 and gamma 2. Okay, this is just a hint, so you can try to solve it and double check. So after you solve this, this is the method we talked. But for the constant coefficient, we can have another way to find the fundamental matrix. So instead of solving for the different initial value problems to find each column of the fundamental matrix, right? We can use an alternative approach. So let's think of a constant coefficient matrix. If you try to differentiate, the second order derivative will be so derivative of ax. But because A is a constant matrix, then that immediately reduces to just derivative of x. And we know derivative of x is A. So this part is ax. So we have A times ax. You see, derivative of x is given in the system. So it is ax. So we simply write it as ax. Then we can see it's a square x. So immediately x double derivative is a square x. So higher order derivative of x can be easily found when A is a constant coefficient matrix. Let's do one more. Third order derivative, right? Third order derivative is just a continued differentiation of the second order derivative. Second order derivative equals this, right? Then third order derivative will be just derivative of this, a square x. And then because A is a constant coefficient matrix, then we only need to find derivative of x. Derivative of x, again, remember it is ax. So let's replace this with ax. Then immediately we have a squared times ax is a third power times x. So we discovered the pattern. When we continue, the pattern will be any order derivative of x. So let's write case, or the derivative of x is just a to the kth power times x. So that gives us any order of the fundamental, actually for the x, the solution of a homogeneous problem. So now if we write our fundamental matrix and we want to determine the fundamental matrix for this problem with constant coefficient matrix, here A is suppose it is a real valued matrix, n by n matrix. And then we can try to extend it as if we write the Taylor polynomials, right, for this matrix valued function. So we can represent this G, for example, at 0. And first derivative of G at 0 and times so t, right? T minus 0, so t times t, and then plus second derivative of g at 0, t squared over 2 factorial plus etc. So kth, or the derivative of t at 0, t to the kth power over k factorial. That's a typical term. So we just try to find the series form for this fundamental matrix. Can we possibly find the series form for this fundamental matrix? What we see here is that the G, you see, evaluated at 0. That's identity. We know it, right? This fundamental matrix at 0 should be identity. What is the fundamental matrix if we take derivative of G evaluation at 0? That is something, think about that one. And also, what about second order derivative of G, the matrix at 0? Case order derivative of G. So these are matrices. Yeah, and at most we multiply the matrix by quantity, right? The quantity. The still, so each term is a matrix, and it's some multiple times that matrix. So the sum is still a matrix. That's the matrix in the series form. So let's think of the fundamental matrix derivative. So very, very similar, because if G satisfies, if G, the fundamental matrix, satisfies the homogeneous equation, then the derivative at 0 is just A times G at 0. So then we can see from the equation the matrix satisfies, we can immediately know the derivative of G at 0, right? At 0 is simply this, which is A times identity, which is still A. Well, it is A, yeah.
So now we have this one. Now how about second order derivative? So we again from the same equation, we can differentiate one more time. We get second order derivative of the fundamental matrix, which is A, the constant coefficient matrix times G first order derivative. Because if we differentiate both sides, right, we get just this. Yeah, so that's what we are doing. After we differentiate both sides, then the G prime, see the G prime is AG, so we can replace this G prime with AG. So we get A times AG, which is A squared times G, which is the fundamental matrix. So this G, of course, this is as a function of T, the matrix valued function of T, but the G second derivative at 0 can be found. As soon as I put a 0 here, then we will be able to evaluate. So let's continue to get higher order derivatives. So next one will be third order derivative at G. So then now we differentiate one more time. Just differentiate both sides one more time. So that is, differentiate above equations. So third order derivative of T equals, and derivative of this, A squared G prime. And again, because G prime is equal to AG, so we just replace it with AG. And then we have A to the third power times G. So we see the pattern. So just like any solution, right? Because X solution satisfies the similar pattern. So then this matrix is a matrix of solutions. So this matrix satisfying the same pattern is not a surprise. So then we can summarize now what is the pattern? What's the pattern? It is, if you try to get case order derivative of the fundamental matrix, it's just A to the case power G at T. So for constant coefficient matrix A, we get case order derivative of the fundamental matrix easily. And so this is a pattern. So then we can evaluate G, the case order derivative of the fundamental matrix at 0 is simply this times G at 0, which is identity. You see, G at 0 is identity. Identity times this, right? It is the A to the case. So we can write as A to the case, since this one is identity. Yeah, that's the identity matrix. Yeah, for this part. Okay, now we are ready to use this. So right now the important thing is we need this case of the derivative of the fundamental matrix. Right now it is found to be A to the power K. And now we substitute this into that series form. So let's put in, so this one is identity, and this one is A. You see, I'm going to replace each part. This one is A. This one is what? A squared. And this case of the derivative of the matrix will be A to the case power. So now we see that we can get the series form of the fundamental matrix. So I'm going to replace this first one with identity, second one with A, right, the term. So let's put this identity, right? If you want to keep the form, it's t to the 0 power, right? So it's okay to put that. So this is A, and then this is a square. Let's replace it with A square, and then continue. So this one will be A to the case. We put A to the case here. That's the case term, right? That's the series form. Now we can write the fundamental matrix into a sigma notation. So let's write a typical term, which is just A to the case power T to the K over K factorial. And K is from 0 to infinity. So you see, I just only include this typical term, and for K from 0 to infinity. Yeah, so that's our power series form for the fundamental matrix. And of course, when K is 0, this you can double check this is T to 0 power. It's just a 1, right? So 0 factorial is over 1. So it doesn't, A to the 0 power is identity, right? That's the first term. Yeah, it's simply the same as identity. So we have, after we have this case, that it means the result that we can use for a constant coefficient matrix, then you can use this as a technique to find fundamental matrix. So here is a matrix that I write as, let's think of a very simple case. So I have A, which is simply the diagonal matrix, right? So let's write this X. Yeah, so this is a very simple problem. The reason I use this simple problem is to show how to discover its fundamental matrix using the series form. And this has the constant coefficient matrix. And we can easily find its power, right? The A is simply a diagonal matrix. And A's power, for example, second power will be just the diagonal entries to the power, to the second power. And you can easily find K's power. So if you want to give the general formula, the K's power, let's revise to the K's power. It's very easy to find any power of this diagonal matrix. So just to the K. So we can find any power of this diagonal matrix. And after we find that, then think of the fundamental matrix. Now we're ready to represent the fundamental matrix. recall that our fundamental matrix for the linear system with constant coefficient matrix is simply that a to the k's power, t to the k's over k factorial. So let me write, okay, the one term, right? So here, a to the k's power already here, and multiply by certain quantity, which is t to the k over k factorial. That's just a number. So I put the -1 to the k, -2 to the k. Okay, what we see here is just this part. You see this part. So this is a quantity, it is here. The a to the k's power is here. And then we add all the terms. So we need to put a sum. Each term is a matrix of this form, k from 0 to infinity. So now, how do you add matrices? So let's continue to go from here to the next step. So we have to add corresponding entries of these matrices. So that, okay, let's look at the entries. Entries is the 2 by 2 matrix. Okay, each entry times this number t to the k over k factorial, right? The first is -1 to the k's. And the other diagonal entry is -2 to the k's. Also, there's a t to the k over k factorial. And that quantity times 0 is still 0, 0. So what I'm doing is just to multiply each entry of this matrix here by this quantity. So now we see this is an entries matrix. And then what we have to add all these matrices, right? From 0 to infinity. And then when we add the matrices, we have we have to add all the corresponding entries. So the first diagonal entry is over factorial k from 0 to infinity. And all those 0 entries will stay 0. And the other diagonal entry will be -2 to the k's, t to the k over k factorial. So now we have the sum. So this infinite series, that means the summation of all these matrices is now reduced to the sum of the corresponding entries. And then we want to see, do we have a limit for this infinite series? So what is this entry exactly? If we can find those entries, and then we have found the fundamental matrix. So the first diagonal entry, let's look at this. It doesn't matter if you put a t to the k's. After that, it doesn't matter. So let's just put t to the k's here just to be consistent, right? So just t to the k's over k factorial. Here is also t to the k's over k factorial. So do we realize what that is? A typical term is given as this, and it's a summation of this. This infinite series will converge to the function
e to the negative t. Because if you rewrite it again, you can discover that diagonal entry is just a negative t. So this is a negative times t to the k's power over k factorial. And k from 0 to infinity. So I'm just simply rewriting negative 1 to the k's, t to the k's, and put together is negative t to the k's power. And then the other diagonal entry is, if we rewrite it, it's easier to see. So it's negative 2 to the k's power, t to the k's. So together is negative 2 times t to the k's power, right? Just rewriting and over the k factorial. And then do the sigma k from 0 to infinity. And the non-diagonal entries will be this. And now it's easier to realize what it is. So this one converges to e to the negative t, exponential function. The other one converges to e to the negative 2t, because you see they are just Maclaurin series for the exponential function. So let's write this infinite series is e to the negative t, and the other infinite series is the e to the negative 2t. And now we have found the fundamental matrix. Fundamental matrix for the system. For this system corresponding to this constant coefficient matrix. A is diagonal. So we just use this as an example to show when the coefficient matrix is a constant coefficient matrix, then this approach can be employed to find fundamental matrix. Yes, the approach is the power series representation for the fundamental matrix.